Take a look at this cattle station in the Western Downs of Queensland. A weathered corrugated iron shed, a timber loading ramp, a line of Hereford cattle resting under a stand of brigalow, and a rusty windmill turning slowly in the dusty afternoon heat. This is the countryside outside Chinchilla, and to anyone driving along the Warrego Highway, it looks like thousands of other grazing properties stretched across the inland plains of eastern Australia. Nothing on the surface suggests anything extraordinary is occurring here. Yet beneath these paddocks, and beneath more than 200,000 square kilometres stretching across southern Queensland and northern New South Wales, lies one of the largest continuous unconventional gas formations on the planet. Geologists estimate the basin holds tens of thousands of petajoules of natural gas locked inside deeply buried rock and coal seams, enough energy to power every household in Australia for decades, sitting quietly underneath grazing paddocks and gravel roads that generations of pastoralists drove across without a second thought. How did one of the most extensive energy reserves in the Southern Hemisphere remain effectively ignored through more than half a century of active petroleum exploration directly through it? And why has this buried geological layer suddenly become the pivot point for the nation's grid stability and next-generation industrial power? Start with the sheer scale of the system, because raw energy figures mean little without spatial context. The primary target across this region is the Walloon Coal Measures, a subterranean formation first mapped in surface outcrops during the 19th century by government geologists who noted its thin, low-grade coal exposures long before anyone conceived of extracting gas from solid rock. It was never a secret that the formation existed. Exploration companies had been drilling straight through these strata since the 1950s, on their way down to deeper, conventional sandstone reservoirs in the Surat and Bowen basins that were far simpler to evaluate and produce. For 50 years, drillers viewed the shallow, water-saturated coal and carbonaceous shale beds as little more than a nuisance, an unstable zone to be cased off as quickly as possible so the bit could reach the target rock below. The productive bands were often only a few hundred meters thick, buried beneath layers of sandstone and clay, which explained why commercial geologists dismissed the formation as an obstacle rather than an asset. By the late 2000s, however, technological shifts transformed the region into the core of Eastern Australia's domestic and export gas supply. Queensland alone grew to produce more natural gas than many energy-exporting nations, drawing its volume from agricultural country, where towns of a few thousand residents were suddenly anchored over global energy assets. To understand how a resource of this magnitude remained unexploited in plain sight, consider the work of the exploration geologists who risked their professional reputations to prove the conventional wisdom wrong. In the late 1990s, small independent exploration teams began re-examining archival drilling logs held by the Geological Survey of Queensland and state mining registries. Old records from earlier oil booms showed that wells drilled near Roma and Condamine had repeatedly suffered gas kicks and blowouts while passing through the Walloon strata, only for the operators to mud off the zones and abandon them as non-commercial waterlogged formations. A small group of persistent geologists studying early pilot projects in North America and applying those concepts to Australian geology realized that the gas was not trapped in structural domes or open porous rock, but absorbed directly onto the internal matrix of the coal and dense shales under hydrostatic pressure. The breakthrough required convincing skeptical corporate boards to spend millions of dollars re-entering properties where traditional wells had failed decades earlier. When early production tests were completed near Fairview and Berwindale, proving that gas could be released at sustained commercial rates by depressurizing the formation, the industry's perception flipped almost overnight. Subsequent geological evaluations by Geoscience Australia and university researchers scaled the estimates upward into massive figures, forcing energy majors to recognize that the unwanted rock layer was, in reality, the primary reservoir. The origin of this vast hydrocarbon store dates back roughly 180 million years to the Jurassic period. A vast freshwater lake and river basin system covered much of eastern Australia, bordered by upland ranges that continually swept fine sediment into the lowland drainage networks. Dense temperate rainforests and peat swamps flourished across the floodplain for millions of years. As plant matter accumulated in stagnant, oxygen-starved water, organic debris avoided normal decay. Buried under kilometers of subsequent sediment, subjected to gradual geothermal heating and tectonic pressure over deep time, those ancient swamp deposits were cooked into coal seams and carbonaceous shales, generating methane that remained trapped tightly within the molecular structure of the rock. Because the gas was distributed uniformly throughout the matrix rather than pooled in localized high-pressure domes, conventional vertical wells drilled in the mid-20th century could not drain it efficiently. The gas sat, confirmed in state survey records for decades, but without horizontal drilling and specialized completion techniques, there was no economic method to extract it at scale. When commercial extraction finally unlocked the basin, the resulting developments swept across the regional landscape at unprecedented speed. Energy consortiums invested tens of billions of dollars across the Western Downs, securing access agreements on cattle properties, constructing compression plants, and laying underground pipelines toward the coast. By 2012, land agents were moving through rural communities that had seen little capital investment for generations, offering compensation agreements to landholders who owned the surface rights while the Crown retained the subsurface minerals. The expansion created a remarkable natural experiment defined by administrative borders. The northern extent of the basin system in Queensland embraced large-scale unconventional gas development, generating substantial regional royalties and regional infrastructure. Directly south, across the state line in New South Wales, public opposition and regulatory moratoriums halted similar developments in regions like the Northern Rivers. Two adjacent agricultural regions, sitting on continuous geological formations, found themselves on entirely different economic and energy trajectories due to decisions made in state capitals hundreds of kilometres away. Economists evaluating border communities a decade later noted stark divergences in local council revenue, infrastructure funding, and industrial activity, even as the subterranean geology remained identical on both sides of the river. Eventually, the rapid surge in gas production altered the regional market dynamics. The construction of massive liquefied natural gas export terminals at Curtis Island near Gladstone linked inland Australian gas fields directly to international spot prices. Local gas prices, which had historically remained low, surged as domestic buyers competed with Asian export markets, while regional field activity adjusted to global commodity cycles. Drilling rigs that had proliferated across Western Downs paddocks thinned out during market downturns, even as the underlying fields continued to produce continuous baseline volumes. Today, the Surat and Bowen Basin operations supply the vast majority of Eastern Australia's gas demand while feeding global supply chains through Gladstone. Pipeline networks managed by operators like the APA Group transport gas thousands of kilometres south towards Sydney, Melbourne, and Adelaide. Yet a new demand pressure is now converging on the grid. The rapid construction of artificial intelligence data centres and high-performance computing facilities across Eastern Australia has created an immense requirement for continuous, firm electrical power. The Australian Energy Market Operator projects industrial electricity demand to rise significantly, with technology infrastructure providers seeking reliable power generation located close to fuel sources. Developers who once prioritised suburban industrial parks are now investigating power connections linked directly to gas-fired generation in regional Queensland, drawn by the continuous energy sitting beneath the black soil paddocks. The cattle property outside Chinchilla remains operational today. The timber ramp, the Hereford cows, and the windmill stand on the surface just as they did generations ago, while far below the topsoil, the dense Jurassic formations continue to supply energy to national electricity networks. The resource was never truly invisible. It was recorded in survey archives for decades by geologists who drilled through it on their way to other targets. It simply required a fundamental shift in perspective to realize that the rock layer long treated as an obstacle was the primary asset all along. To understand why the full extent of this energy reservoir took more than a century to be recorded in official survey literature, one must examine how the geology of the Australian continent was mapped in the first place. For tens of thousands of years, traditional owners lived across the Surat and Bowen basins, reading the surface landscape, its river systems, and soil changes with total precision. What was absent before the late 19th century was not human awareness of the terrain, but the institutional record, the geological cross-section, the bore log, the official map sheet, and the corporate prospectus. When colonial surveyors began grid-referencing Queensland in the late 1800s, they evaluated the land almost entirely by what could be seen from horseback or extracted with surface shafts. They looked for high-grade coal seams, outcropping metal lodes, and permanent surface water. The deep, tight carbonaceous shales and thin, water-saturated coal bands buried hundreds of meters below the topsoil were invisible to their tools. The sequence that produced this subterranean system began during the Middle Jurassic epoch, approximately 180 million years ago. At that time, Eastern Australia was situated further south than it is today, forming part of the eastern margin of the Gondwana supercontinent. A vast structural depression, now known as the Surat Basin, covered an area exceeding 270,000 square kilometres across what is now southern Queensland and northern New South Wales. The climate was cool and humid, supporting sprawling river deltas, expansive lakes, and peat-forming swamps that covered thousands of square kilometers. Over millions of years, millions of tons of organic plant material accumulated in stagnant, low-oxygen swamp waters, preventing rapid oxidation. As the continent shifted and tectonic subsidence lowered the floor of the basin, layer upon layer of river silt, sand, and volcanic ash washed down from rising highlands to the east, burying the organic peat under thousands of meters of heavy sediment. Under mounting lithostatic pressure and geothermal heat, the peat compressed into the coal seams and carbonaceous mudstones of the Walloon Coal Measures. Methane generated during this thermal maturation process did not escape to the atmosphere. Instead, it was forced under immense hydrostatic pressure directly into the micropores and cleat networks of the coal itself. The rock acted simultaneously as the source, the seal, and the reservoir. When modern exploration began in Australia following the Second World War, geologists from the newly formed Bureau of Mineral Resources, the predecessor of Geoscience Australia, focused on finding conventional petroleum structural traps. Companies like Associated Australian Oilfields drilled dozens of vertical exploration wells across Queensland in the 1950s and 1960s, targeting porous sandstone domes where gas or oil had pooled in open cavities. Whenever their drill bits punched through the Walloon Coal Measures, the sudden release of pressure caused methane to bubble into the drilling mud. In dozens of official bore reports filed with state archives, these events were logged as brief gas shows, but ultimately dismissed as dangerous drilling hazards. The rock was too tight, the coal seams too thin and broken, and the water content too high for traditional vertical wells to produce gas at steady commercial rates. For 50 years, the standard engineering procedure across the basin was simple. Drill through the coal as quickly as possible, cement the casing across the interval to seal off the water and gas, and push deeper to the traditional targets. The official record had logged the presence of the formation, but the technical interpretation framed it as a barrier rather than a resource. It took a fundamental shift in global petroleum geology, combined with the arrival of directional drilling and precise hydrological management, to demonstrate that the very rock being cased off held more energy than the deeper sandstones beneath it. How did a small team of persistent geologists manage to turn decades of discarded government drilling archives into the foundation for a multi-billion-dollar energy industry? The shift in understanding began not with a sudden flash of insight, but with a systematic re-examination of physical drill core samples held in state storage facilities. At the Geological Survey of Queensland Core Library in Zillmere, tens of thousands of meters of rock core, extracted during mid-century exploration runs across the Surat Basin, had sat in metal trays for decades. Geologists re-evaluating these samples in the late 1990s stopped looking merely at the permeable sandstone units and began subjecting the intervening coal seams and dense carbonaceous mudstones to modern analytical techniques. Isotope geochemistry and gas desorption testing revealed that the coal matrix contained significant volumes of methane per ton of rock, gas held under pressure within the microscopic pore structures of the coal itself. The key diagnostic tool was two-dimensional and three-dimensional seismic reflection survey data. In early regional surveys, seismic waves generated at the surface reflected strongly off major structural boundaries, but the fine, interstratified coal bands of the Walloon Coal Measures caused wave scattering that made the formation appear as noisy, low-amplitude acoustic interference. Modern processing algorithms, introduced around 2002, allowed geophysicists to filter out surface noise and isolate the subtle impedance contrast between the coal seams surrounding shales and water-bearing sandstones. When combined with wireline logging tools lowered down freshly drilled boreholes, specifically density logs, gamma-ray detectors, and acoustic velocity tools, the data provided a detailed profile of the target formation. Geologists could map continuous seams ranging from a few centimeters to several meters thick across hundreds of kilometers of subterranean country. Airborne laser scanning, or LiDAR, alongside high-resolution satellite imagery, added another layer of confirmation. While the gas reservoirs themselves sat hundreds of meters underground, microfracture patterns and regional fault lines had subtle surface expressions. Digital elevation models built from airborne laser surveys surveys identified linear terrain features, joint systems, and minor surface displacements that mirrored the underground fracture networks. By mapping these structural alignments across regional councils like the Western Downs and the Maranoa, resource geologists could predict where natural fracture pathways would allow gas to flow more freely through the low permeability rock when stimulated. Geochemical sampling of fluid samples drawn from historical water bores across Queensland provided further empirical proof. Hydrocarbon gas chromatography confirmed that the gas was predominantly thermogenic methane, generated by deep thermal cracking of organic matter over millions of years, mixed with secondary biogenic methane produced by bacterial action in the shallow aquifers. The isotopic signature of the carbon atoms in the methane proved that the gas was generated directly within the coal seams rather than migrating up from deeper regional formations. Despite these advanced technical tools, the survey data revealed clear limits to what was known. While gross rock volumes could be mapped with high precision across vast areas, local variations in permeability, gas saturation, and coal cleat density meant that reserve figures remained estimations within broad confidence intervals. Government geological surveys, including Geoscience Australia, continuously adjusted baseline estimates as thousands of new appraisal wells provided physical core data to calibrate the seismic models. The mystery was never that the rock was hidden, it was that the methods required to map its internal fluid mechanics did not exist when early surveyors first crossed the surface. But as the physical boundaries of the reservoir were finally confirmed across Queensland and New South Wales, what were the immediate, tangible consequences for the farms, small towns, and national supply lines sitting directly above it? Today, the reality of this subterranean industrialisation rests directly on top of agricultural land, regional infrastructure, and local water systems across southern Queensland. More than 20,000 production wells have been drilled across the Surat Basin alone over the past 2 decades. What appears on the surface as an ordinary cattle property or grain paddock is frequently traversed by underground gathering lines, access tracks, and wellhead pads. The surface infrastructure remains low profile: a gravel pad, a wellhead assembly, and a metered valve set, yet the collective footprint covers thousands of square kilometres. The primary physical challenge is not the gas itself, but water. To release the gas trapped within the coal matrix, hydrostatic pressure must be lowered by pumping out large volumes of ancient groundwater stored within the coal seams. The volume of co-produced water extracted across the basin is significant. Industry and state government reports record that tens of gigalitres of groundwater are extracted annually during field operations. This water, sourced deep within the Great Artesian Basin system, is typically saline and requires industrial reverse osmosis treatment before it can be used for agricultural irrigation or discharged into local river catchments under strict environmental licenses. The Office of Groundwater Impact Assessment in Queensland maintains continuous hydrological monitoring across hundreds of observation bores to track changes in water pressure across adjacent aquifers used by local pastoralists. While data indicates that drawdown is concentrated primarily in the coal seams themselves, long-term connectivity between the Walloon Coal Measures and overlying freshwater aquifers like the Precipice sandstone remains an area of ongoing scientific evaluation and active monitoring. The economic and structural impacts across local government areas like the Western Downs Regional Council and Maranoa Regional Council have been profound. During the initial development phase between 2010 and 2016, regional centres like Chinchilla, Miles, and Roma experienced intense economic shifts. Housing costs escalated rapidly, local businesses expanded to service infrastructure contracts, and council road networks were upgraded to handle heavy transport vehicles. When field construction transitioned into long-term operational phases, regional activity settled, leaving small communities anchored to high-volume energy exports. Beyond local impacts, the gas extracted from these former obstacle rocks now underpins national grid operations and regional manufacturing. Gas-fired power stations along the eastern seaboard rely on steady supply from the Surat and Bowen basins to maintain grid frequency and meet peak demand periods as coal-fired plants retire. The integration of high-demand digital infrastructure, such as major data centres planned across Queensland and New South Wales, adds further demand to this subterranean resource. What began as a neglected geological layer in mid-century drilling logs has become an infrastructure anchor for national energy networks. What does this long history of overlooked geography tell us about the remaining blind spots on the map of Australia? The story of the Walloon Coal Measures and the Surat Basin shows how easily a primary continent-scale feature can hide directly beneath ordinary pasture. The formation was never truly absent from map sheets or exploration archives. It sat recorded in government geological surveys, university repositories, and drill logs held by state registries for more than 50 years before its true capacity was understood. What kept this vast reserve hidden in plain sight was not a physical barrier or a lack of surface evidence, but a fundamental technical assumption that equated high water saturation and low matrix permeability with geological worthlessness. Industry practice defined a reservoir strictly as porous rock where fluids flowed freely under natural pressure, and because the Jurassic coal seams failed that single test, generations of engineers cased them off without further analysis. Significant scientific and environmental questions remain unresolved across the basin today. Researchers from CSIRO, Geoscience Australia, and state environmental departments continue to track long-term hydraulic impacts, monitoring how multi-decade depressurization of deep coal beds affects regional groundwater movement across adjacent aquifers. Questions regarding long-term subsidence, baseline methane seepage rates through natural fracture networks, and the full extent of microseismicity are still being investigated using regional seismic networks and satellite radar interferometry. The geological record is never static, and the full long-term behavior of these deep sedimentary basins under continuous extraction will take decades of further observation to completely comprehend. The official map of Australia often looks complete, fully drawn with precise state borders, road networks, and municipal boundaries. Yet beneath those lines, buried under hundreds of meters of weathered soil and deep sedimentary cover, the physical reality of the continent continues to surprise the institutions that attempt to map it. Which geological feature or landscape anomaly in your own state or territory has always struck you as widely overlooked or misread? Let us know in the comments below, and consider subscribing to follow our ongoing investigations into the overlooked geography of